Okay, so in the first part of in the first part of calculus, we concerned ourselves with the instantaneous rate of change, the slope of a tangent line, and those type of things. And we talked about derivatives. We talked about df dt, dy dx, y prime, these kind of things. Okay, and in the second half, we are going to concern ourselves with what is called the integrals. Okay. Okay, so chapter 6 has 5 sections, and we're going to go ahead and plow right through. We're not going to cut this in half. We're going to go 6.1 all the way through 6.5, and then we'll have just one test. Okay, so we will not have a quiz for chapter 6. All right, so 6.1, here we go. We're talking about estimating with finite sums. So this week, today we're going to do 6.1, and on Wednesday we will do 6.2. Okay, 6.1, estimating with finite sums. Okay, estimating with finite sums. So let's go back to way back when we talked about traveling from, I don't know, let's say we're driving at 60 miles per hour. So this is the velocity. This is the time, and we're traveling at a constant rate of 60 miles per hour. Okay, and let's say that we traveled from time equals, we want to find out from time equals 5 to time equals 7. So how many miles did I travel? Okay, if I went from 5 o'clock to 7 o'clock, okay, so I traveled for 2 hours. How long did I travel? What was the distance that I covered? Anybody tell me?
120 miles.
120 miles, right? We got 60 miles per hour, and we traveled for 2 hours, correct? So the hours cancel out, and we're going to end up with 120 miles, okay? Now, graphically speaking, that would be the area under the curve from 5 to 7. This area here is going to be 120 miles, okay? So 120 miles. So we're talking about area under the curve, okay? Area under the curve. And this is what we're going to concern ourselves with in the second half. Now we're going to talk about area under the curve, okay? All right, so let's go ahead and flip down to example number 1. And let's talk about calculating snowfall. Okay, calculating snowfall. So example number 1 on page 270, example number 1, we have, consider a snowstorm that starts at 3 a.m. Over the first 2 hours, the rate of snowfall increases from 0 to 1.2 inches per hour. Okay, so this here is going to be the snowfall rate, and this is going to be time. Okay, so from 3 o'clock to 2 hours to 5, it's going to go from 0, no snow, to 1.2 inches per hour. So 1.2 inches per hour. So we'll go from here to 1.2 inches per hour. And then it's going to continue to fall at the constant rate of 1.2 inches per hour all the way till from 5 to 8 o'clock. Whoops. Trying to draw a straight line here. 8 o'clock. 8 o'clock. And then from 8 to 10:30, at 10:30, it stops snowing, okay? Again, so what we want to find is how much snow has fallen during this time, okay? So it's very similar to the miles per hour over time. Snowfall is going to be the rate of snowfall, 1.2 inches per hour. Then we're going to times it by the time, right? It's going to be the times the time. Okay. So from here to here, we're going to calculate the area under the curve, which is nothing more than a triangle there, right? So the area under that curve is going to be what? What is this going to be? Luke, tell me what the area under that curve is.
1.2.
How did you get that?
2 times 1.2 divided by 2.
2 times 1.2 divided by 2, right? The base, 2, and the height is 1.2 divided by 2. And then we can get, now we're going to try to find this area here. What's this area here? Anybody? That's just
3 times 1.2.
1.2 times 3, right? The base is 3 and the 1.2. And again, here, over here, we're going to get 1.2 times 2.5, 2.5, 1.2 divided by 2. And we're going to add them all together. Okay, so you're going to get 1.2 plus 3.6 plus 0.6, 15, 1.5. We add together, we're going to get 6.3. So we're going to get 6.3 inches. Okay, again, area under the curve, right? Area under the curve. All we're doing is that. So this is fine. Okay, this is easy when the area or the area that we're trying to find are either, you know, triangles or rectangles or something very geometric so that you can go ahead and just go ahead and calculate it, right? That's fine. The problem is when you get curves like y is equal to x squared, and you want to find the area underneath that from 0 to 4. Okay, now we're going to have a problem, right? Because we can't really, there's no geometric shapes here that we can calculate. Okay, so the way we do this is we're going to go ahead and so we're going to estimate it. We're going to partition this graph. We're going to partition it in 4 partitions. So equal partitions. So we have 1, 2, and 3. So you're going to have 4 sections. You have this section, 1, 2, 3, and then you have 4 different sections, okay? So let's try to calculate the area between 3 and 4. So how would you calculate this strip here? Okay, so here's where the problem comes, all right? So we do not know what to use as for height goes. We know what the base is. We do not know what the height is, okay? So the way we do that, if you flip the page, okay, is that you can do, there are 3 different ways, okay? So we're going to talk about the left area. So what we're going to do is that when we do the height, we can either choose the one on the left or the one on the right. Okay, so for this specific one, if I choose to use the left-hand point as the height, and I calculate something here, what would I calculate? I would calculate from here to here, correct? So am I underestimating or overestimating at this point?
Under.
You're underestimating because you're not counting this portion up here, right? So I'm going to be underestimating it, right? But that's okay. That's what we're gonna do. Okay, so in this one, I'm going to say, since we're using the left-hand side, this point is going to be what? What is the height here? When x equal to 3, the height is going to be
9.
9, right? So I'm going to go 9 times 1. 1 is the base, so that's the area there. That's what I calculated. Okay, so the one over here is going to be what? Again, I'm going to go to the left-hand side, right? So left-hand side is going to be what?
4.
It's going to be 2, it's going to be 4, right? It's going to be 4 times 1, And over here, I'm going to do the 1, right? So what's 1 going to be? 1, right? And these are all the bases. The bases are all the same, right? Because they're equal partitions here. What's this guy over here going to be? The very last one. Zero, right? Because I'm going to use the left-hand side height for height, and the height at the left-hand side is going to be 0, correct? Let's say, so that was the left hand. What if I do the right-hand side? What if I choose the right-hand side? Okay, so let's go back to the initial one, this one over here. What is the right-hand side? It's going to be up here, right? So what's that going to be? 16 times 1, right? Now for this one, what is the right-hand side going to do? It's going to be this guy here. So 3, when it's 3, it was 9. And this guy, the next one over here, if I use the right-hand side, it's going to be 2 when it was 2. So it's going to be 4 times 1. And over here, the very last one, it's going to be what? 1 times 1, right? So obviously, this guy here, when I add them all up, I'm going to get 9, 4, 1, so it's going to be 14. If I add this guy up, I'm going to get 20, 30, right? Big difference, depending on which side I use, right? Now also, I can use the midpoint. Okay, so let's do the midpoint here. Okay, so the midpoint is going to be what? What am I going to use there for midpoint?
3.5.
I'm going to use 3.5, so it's going to be 3.5 squared times 1. This guy is going to be, or what the next one's going to be 2.5 squared times 1. It's going to be 1.5 squared times 1, 0.5 squared times 1. Anybody want to add that up for me? What is 3.5 times 3.5?
12.25.
1. So this would be 21.
21. Oh, you beat me to it.
21, right? So 21, all right, 21. Okay. So, it's not times 1. So you get, so if I use the left-hand side for the height, I get 14. If I use the right hand for the height, I get 30. And if I use the midpoint, I'm going to get 21. Okay? So this is just the estimate. Now, do you think that I would get a better estimate if I increased the number of partitions or not? Would I get closer to the actual if I increase the number of partitions?
Yeah.
I would, right? Because I would get smaller slices, and therefore I would get smaller errors, correct? In other words, this one we found that we were underestimating. This guy was overestimating, right? And this one we're not sure. Okay, and so that is what we call the rectangular approximation method. Okay, so this is what we call the LRAM, left-hand rectangular approximation method. This we call the RRAM. And this we call the NRAM. Okay, so if you go to your calculators and now open up the program, RAM, you have a program called RAM there, correct? Everybody find it?
Yeah.
Okay, so for the equation, you're going to put y is equal to x squared, right? And then I think it asks for the boundary, right? 0 to 4. We're going from 0 to 4. That's what we're trying to estimate, the area under the curve from 0 to 4. Then it's going to ask for partitions. Put in 4. And if you hit execute, you should get the LRAM, RRAM, and the MRAM. Did you get those?
Just says start and then end.
Start is 0, end is 4.
And it says number sub int.
Yeah, number of subintervals, number of partitions, that's 4.
And then it's an error.
What?
There's no place to put the equation in. Do we have to do it
You
in?
have to put the equation in the y equals x squared. You have to put y1 equals x squared. I'm sorry, my bad.
Wait, where do we put the equation in?
In your graph section where it says y is equal to whatever, right?
Oh, okay. Thank you.
Oh, I got it. 14, 21, and 30.
14, 21, and 30, right? So you got the LRAM, MRAM, and the RRAM, okay? All right. So that was when the subintervals were equals to 4, right? When you had 4 subintervals, all right? So now let's go ahead and increase that to n equals to 10. What do you get? Logan, are you getting anything?
Uh, 18.24.
That's the LRAM.
Yeah, the mid is 21.28.
Uh-huh.
The right is 24.64.
Everybody else get that? Let me know if you didn't get it. I need to know if you didn't get it. Okay, because you're gonna have to do this in your homework. All right. So as you can see what happens when we go n equals 10, you can see that the difference is getting closer, right? We're getting a smaller error, right? Right? So it's gonna be somewhere in between here, right? The LRAM and the MRAM, right? And LRAM and the RRAM, right? Okay. Are we good? What about n equals 50? What do you get if n equals 50? What was the LRAM?
20.6976.
Okay. RRAM?
21.3312.
Okay.
And then 21.9776.
21.9776. Okay, so this, I got these switched then. What was the MRAM again? 3312? 21.331?
I think those two are switched.
What was the MRAM? What was the middle number?
It's the 21.3312.
Because I got this switch, because I got LRAM. Your reading comes LRAM, MRAM, and RRAM. Okay, so that's why mine are switched. It looks like they're switched. Okay, all right. What if you do n equals 100?
They're all within 21.
You're all 21.
They're like,
21.3333.
yeah,
I hope, right? So what do you expect if you were to guess, if I did this without estimating and actually calculate it, if we knew how to calculate it, what do you think the number is going to be? What do you think the number is going to be? It would be this, wouldn't it?
yeah.
1/3, isn't that basically what it looks like? Right, if you were to guess. Okay, and we'll find out what that is later, what this is later on, okay? We'll find out later on, okay? But this is how you would do LRAM, MRAM, and RRAM, okay? So can I say that LRAM is always going to underestimate and RRAM is always going to overestimate?
Yeah, well, I mean, unless you keep making the number bigger, then it gets close.
Yeah, as I increase the number of subintervals, that they're going to get closer and closer. They're going to converge to the correct answer, correct? What if the graph did not look like this, but the graph looked like this? Now, if I do the subintervals like I was doing before, right? If I do the RRAM, am I doing an underestimate or an overestimate?
Under.
I would underestimate, right? So it'd be the complete opposite here, correct? Right? Let's say that y is equal to minus x squared plus 4. Go ahead and change that. Change your equation to y is equal to minus x squared plus 4 and leave everything the same and do n equals 4. You're going to get a larger number now on the LRAM side. And why does that happen? Can anybody tell me? How sometimes it is overestimating when it's LRAM and sometimes it's underestimating?
Well, isn't it just the slope?
Kind of, a little more specifically. You're on the right track.
Increasing or decreasing?
Correct. It's an increasing or decreasing function, right? Because the function here is increasing, which means that always the R, the right-hand side is going to be larger than or longer or taller than the left-hand side, right? Where on a decreasing function, it's the exact opposite. Can you see that? Right? So don't think that LRAM or RM automatically over or underestimates, okay? Because you're going to get sometimes you're going to get functions that look like, that are not pretty like this, but sometimes you're going to get functions that look like this, right? So sometimes it's going to be, if I go from here to here, sometimes it's going down, sometimes it's going up. And so basically you can't really say, right, conclusively that it's going to over or underestimate. Well, the only time you can actually say that is if it's a continuously decreasing or continuously increasing function within the bounds that we're looking at. Okay, all right, so just keep that in the back of your mind. All right. So let's go to example number 3 on page 273 and see if we can use this. So on page 273, the function that we're looking at is y, this is example number 3, y is equal to x squared sine x. And we're going from 0 to 3. Estimate the area under the curve from that to that. Okay, so let's do n equals 50. And give me what you found for L, M, and RM.
Well, it shows you in the book.
I know, I just want to make sure that you can regenerate or reproduce the same numbers here using your calculator program, right? Don't you feel so nice that you're finally using the program in the calculator that we've been harping on?
That is true. I was
Okay.
wondering.
Because some of us actually worked hard to get that done, right? Right, Sam?
Yeah, it took a couple days to figure it out.
Okay, so let's do n equals 50 and see if we can actually reproduce the LRAM number of 5.7 3615. MRAM is 5.77788. And over here we have 5.81235. So see if you can reproduce that. Everybody get that? Give me a thumbs up if you got that.
I got it.
Anybody else? Luke? Caden? Logan's got it. Logan, you got it? Did you get a new calculator?
No.
Or are you just putting that thumbs up there for no apparent reason?
I put my thumb up so you know I was still here.
You're just still there. You're participating. You're trying to without the calculator. Is that what's going
I
on?
tried so hard with this stupid platinum thingy.
Oh, okay. All right. So, but everybody was able to get that, right? I'm assuming that everybody got that. You everybody get this? Were you able to get that? Christina, did you get it?
Actually, I failed to install the apps. Like, I think this is the one that we use apps, or is it the one we just use the calculator?
This is the one that we use the calculator for. Yeah. So it's a
Oh,
one of the
not
programs.
the apps.
You got it?
Oh, is it like, can we do it only the calculator, not the apps?
Oh, in the apps. I don't know anything about the
Oh,
apps. Okay. All right. So you should have been able to get this. Okay. So I'm going to assume that everybody's able to get that. And we are going to stop right here and we will finish the rest up in the second half. Okay. So, oops, where am I at?